Okay, so we have here another problem with this spherical tank. So we have 1.8 meter diameter spherical tank with negligible thickness, which contains iced water at 0 degrees. Here at 25 degrees Celsius flows over the tank with a velocity of 7 meters per second. Determine the rate of heat transfer to the tank and the rate at which the ice melts. So the heat of fusion of water at 0 degrees Celsius is 333.7 kilojoules per kilogram. In here we have an assumption that it has negligible thickness. But what basically means is that well, realistically it has a thickness, right? So it has conduction, no? So convection and conduction, and then conduction within the fluid. So we are assuming that this thickness right here is infinitesimally thin, no? For a reason that the conductive heat transfer is negligible. Okay, so this will be purely convection in a spherical tank. So we need to find here first, to find the Q, no? So to find the Q, we need the H. To find the H, we need the Nusselt number. To find the Nusselt number, we need the Reynolds number, the Prandtl number, every other properties, no? So remember that we have a spherical tank or any sphere, no, convection. It is evaluated. The properties are evaluated at the infinity. Except for dynamic viscosity. So for dynamic viscosity, you need the surface temperature. Okay, so let's begin. So we have a free stream temperature of 25 degrees Celsius. So we will choose that as our um as the properties for calculating the Reynolds number and everything else, no? And then we only need the temperature of the surface, which is 0 degrees Celsius, for the dynamic viscosity, which is where is it? Which is this one. Okay. So in order to find the Nusselt number, we need the Reynolds number and the Prandtl number, no? So we need to find the Reynolds number. No? So the Reynolds number here will be just V T over viscosity, you know. So the velocity is 7, no? 7 meter per second. Diameter is 1.8, and then the kinematic viscosity, no, is 1.849, no? Okay? Huh? Sorry, the kinematic pala, no? Kinematic is 1.562 times 10 to the negative 5. Okay, so this will be in meter second squared for the numerator, meter squared per second, for the denominator. So this will be dimensionless. So you have your calculator. You need your calculators. So you have 7 times 1.8 divided by 1.562. That's to the negative 5. Okay, so you have 806,658, no? So 806,658. I mean, you can write that down, but to make things a bit more compact, what you can do also is use the English notation, the scientific notation, no, using this ENG button here. So you have 806. I just write down 4 significant figures, but you can include more than 4, no? Significant figure. So 806.7 times 10 to the 3, no? Okay. And then for the Prandtl number, this is already given, so we can find the Nusselt number, no? So for the Nusselt number, I'll just look at my notes here. So the Nusselt number for sphere is 2 plus you have 0.4 RE raised to 1 half, and then plus 0.06 RE raised to 2/3, and then Prandtl number raised to 0.4, and then multiplied by the ratio of their viscosities, no, or dynamic viscosities, mu s, and then raised to 1/4. Okay, so we can calculate everything. So we have the Reynolds and the Prandtl number given, and then we can equate this to HD over K, right, for the Nusselt number. So we can find H already by I'll skip to the parts, no, so that we can just find the H. So the H here is I need to rewrite this really, no? So H is equal to K over D multiplied by this, no? So 2 plus 0.4 or E Reynolds 1/2 plus 0.06 Reynolds 2/3, and then Prandtl number ratio of their dynamic viscosities. I need to make things a little bit smaller. Okay, I think that's it. To find the H here. So you can find H directly. I'll just use my calculator. Just use my calculator directly to input the values, no, so that we can save a little bit of time. So you have K here. K here is at T infinity, no? So we have 0.02551 divided by the diameter is 1.8. Then you have 2 plus 0.4. Reynolds number is just input A here for Reynolds number, guys. No, you can do this as well so that you can change the Reynolds number dynamically. 0.06 Reynolds number, 2/3. Prandtl number. So Prandtl number, I'll just write here B. Do you have the 2 there? Okay, we have the 2. Okay, and then raised to 0.4 and multiplying this by the ratio of the dynamic viscosity. So U infinity 1.894849. So they're both raised to -5. So I won't write the no, they will just cancel out the scientific notation. So 1.729 for the surface, and then raised to 1/4. Okay, I think that's it. So you can find H, that is 9.67. Okay. Since I might we forgot to substitute the value, sorry. So 806.7 times 10 to the 3 for the Reynolds number, and the Prandtl number is 0.7296. Sorry. So 11.20. Okay, 11.20. Yes, no? So 11.20 watt per square meter Kelvin. So we have the H. We can now solve for the Q. So the Q convective is just, again, H times the temperature difference, no, and the area. So HA times the temperature difference, which is just the T infinity minus Ts, no? So in here, the area of a sphere, no, remember that the area of the sphere is, you can use pi r squared times 4, or you can also use pi d squared. So the given here is the diameter, so we can just use pi d squared. So you have 11.20 times the area times the temperature difference. You can solve for Q con. So the Q, the heat transfer rate is I'll just use answer, and then you have pi times the diameter squared for area. So this is in square meters multiplied by the temperature difference. So 25 minus 0. So the heat is 2849.62. No? So we just have a little bit of 28, a little bit of rounding errors. No? So we have in watts. Okay. So now for the rate at which the ice melts. So I think at this point you're already familiar with latent heat, no? So for latent heat, so remember that Q latent, no, this is equal to the mass flow rate, no? The mass that is it could be changing phase, no? Times the latent heat of vaporization. So in this case, the latent heat of vaporization of water at 0 degrees is 333.7. No, actually, it is latent heat of fusion because it is from liquid to solid. But if it is from liquid to gas or gas to liquid, it will be latent heat of vaporization. So in this case, to find the mass flow rate, this is just Q over L, no? So Q here is the Q convective, no? There's no other heat transfer here, and then over the latent heat. So this will be just 2849.62. So this is in kilojoule per in joule per second divided by what is the latent heat? So latent heat is 333.7. So in here I can just so this is the different units, no? So you have here kilojoule per second, sorry, joule per second only pala, no? Joule per second, which is in watts, no? And then you have 333.7 kilojoule, no, per kilogram. So we want to cancel the joule. So we have to multiply this by 1,000. So you have 3337, no? So you have 1, 2, 3, no? So you have this much zero. So 333,700 joule per kilogram. So that we have an answer in kilogram per second, no? Okay. I'll just write this in red, no? So joule per kilogram. So the mass flow rate in kilogram per second can be found. So answer divided by 333,700. Okay, so you have 8.53 or 8.539 times 10 to the negative 3 kilogram per second. So we can convert this into per hour by multiplying 3,600, no? So you have 30.74. So either way, no, if the unit is not really explicitly asked for, it can be either, no, you can have an answer of in kilogram per second or kilogram per hour. But I believe the reason behind the answer key is in kilogram per hour because the value in kilogram per second is very small. Yeah. Okay. So that's it. Thank you guys for listening. First, Streamlabs.